Hello everyone. Today we will start one new topic which is tensile testing. In last classes what we have seen, we have discussed that the yarn characteristics we can test by its linear density, or there are various other characteristics. Fiber characteristics we have seen, which we have seen that by length we can express, we can measure the length and related characteristics, length variation. Then we have seen that the fineness of yarn we can test by various methods, and maturity of cotton we have discussed, and then linear density of yarn. Now, in this topic we will discuss the tensile testing. Here tensile testing, it is actually divided into three distinct categories. One is in the tensile testing of fiber, next is tensile testing of yarn, and then tensile testing of fabric. So, three different measurement techniques, but if we see the basic principles, basic theories of all these three types of testings are almost same. We get similar parameters. We will discuss all these aspects in this session. So, why tensile testing of textile materials are important? Okay. So, why do you know, why do you want to know the tensile characteristics? It is just to know the level of strength provided by the material. Okay. What is the strength of the material? Okay. That we must know, because at which load it will fail, that it must know, but that particular value, it is very important for industrial and technical products. Okay. This is very important, because in those applications this strength breakage of material, it is extremely, we should know that it is extremely important to know, because that, like let us take example of rope. In rope, if we do not know the its breaking strength or stress strain characteristics, then it may fail during its actual use. So, any industrial application like filter fabric or maybe geotextiles, we must know the strength characteristics, its breaking strength, its elongation. So, all these characteristics we must know, but for apparel application, household applications, so this importance, although we must know the tensile characteristics, but its importance is not that, as in case of industrial textiles. Okay. So, because in household or apparel we never apply that level of force where it breaks. So, merely it is needed to, for adequate strength is needed. So, in during handling it should actually the product should not fail. Okay. In order to withstand handling, during production and use. Like we need that much strength of yarn, so that it should not break during weaving. So, that much. So, if we have excess strength by imparting, by using various very sophisticated, very actually high tenacity fiber, that means we will unnecessarily add to its cost. So, for fabrics for apparel application, we do not need that much strength, but for technical application, definitely for like composite making, we must use yarn or fabric with very high strength. So, in those applications, it is extremely important to know the actual strength, even strength related characteristics. Now, let us see what are the factors which affect the strength of textile materials. First is that molecular structure of fiber. So, if the orientation, molecular orientation is high, then its stress strain characteristics will totally different, will change. So, higher molecular orientation will result better strength characteristics. Number and intensity of weak places. So, if the weak places are high, so basically strength of any material is the strength of its weak point. So, a yarn with say lower mean length, let us see this is the mean value. Okay. One yarn, this is the length along the yarn, okay, along the yarn. Suppose this is one yarn, even yarn, okay, even yarn, yarn A, another yarn which is uneven one, yarn B. Now, the yarn A has got, this is the strength value, okay, breaking stress. So, this yarn A, if we see theoretically at each and every point, okay, that the strength, it will be approximately same, because this yarn is uniform and number of fibers in the cross section of the yarns are same. So, this yarn has got almost uniform strength along the length at different point. If we test strength here at this point, at different point the strength will be almost same, but if we test the yarn B, suppose this yarn we have produced with a very good fiber, it is a very strong fiber. So, at different point this yarn strength will be different. Suppose mean strength is very high, okay. So, strength is higher than the strength A, strength of yarn A. So, but what we have observed that few points where due to unevenness there will be weak points are there. Okay. So, few weak points are there, and when we test, it does not matter the other places, it is very strong, it will break only at the weak point. So, that is how the yarn will fail. Okay. So, the number and intensity of weak places will result weaker yarn. Okay. So, that is why the yarn which is uniform yarn with relatively lower strength is preferable, okay, and which is better than the yarn with higher mean strength, but it is non uniform. Coarseness or fineness of fiber. So, coarser fiber will result, just let us see. So, cross section of two yarn, okay, A B of same count. Yarn A is made of the coarser fiber, and yarn B is made of fine fiber. The linear density of these two yarns are same, as this yarn B is made of finer fiber. So, number of fibers are more, and also the specific surface area, surface contact of fibers in yarn B is much more than yarn A. So, that due to the finer fiber, so the yarn strength realization will be more in case of B. Third factor is relative humidity and temperature. So, as we know, textile material, most of the textile materials absorb moisture, okay, the hygroscopic in nature, and there are fibers like cotton, which with the increase, with the absorption of humidity, the strength increases. But on the other hand, fibers like viscose rayon, after absorbing moisture, the strength drops. So, the relative humidity of the during testing, if it varies, then the for same yarn we will get different results. And also temperature, although not directly affect, but if it is too high temperature, very high temperature, then fiber may get degraded and it affect the strength. Also it is too low, at too low temperature, say sub-zero temperature, at that temperature. So, sometime few polymeric fiber, they may be brittle and it affects the strength characteristics. So, relative humidity and temperature we must maintain. So, that is why it is suggested that to test the yarn or any textile material under standard atmospheric condition. Next is the elasticity. Elasticity also affect the strength characteristics of material. We will discuss all these characteristics. When an external force is applied to any material and it is balanced by the internal force developed in the molecular structure, okay, that is how we get stress strain characteristics. Man-made fibers are usually tested for their individual strength. So, the fibers we can test in two ways, in the single form and in the bundle form. Okay. So, most of the man-made fibers we get in the long continuous length form, that is why it is easy to test in the individual fiber strength. Okay. We can test, as there is a very less variation in length and fineness of the. So, it is available in a long fiber and continuous condition, and in the man-made fiber another advantage is that it is a uniform in nature and in terms of fineness. Okay. So, as we have seen earlier, so this is a man-made fiber. Okay. And another is it is a natural fiber like cotton. Now, it is easy to test the fiber in the single fiber form. the advantage of man-made fiber is that its diameter wise towards the length wise it is totally uniform. Okay. So, across the total the diameter, the cross sectional shape or diameter is same throughout the length. But in case of cotton it varies. So, if we test the cotton in single fiber form, so it will always break at the weakest point, because variation in diameter, so variation in all these parameters fineness. So, it will always break in its weakest point. So, we will end up with a value which is much lower than its capability. And another reason is that here in man-made fiber, as I have mentioned, that it is available in continuous form. So, to minimize this variability, what we must do? We must take a number of fiber together. So, bundle of fibers we take together and then we test, like in bundle form. Suppose this is a cotton, we do not test the fiber in single form, because it is also very difficult to handle a single fiber of short length. Instead of that, we take a bundle of fiber, this is type bundle, then try to break the bundle and try to measure the bundle, and after that by simple calculation we can convert it to fiber tenacity, fiber strength characteristics. So, natural fibers are tested for their bundle strength due to high variation in terms of length and fineness. So, that is the reason why natural fibers are tested in bundle form. It may be cotton, may be jute, different natural fibers. Okay. So, in bundle strength, a bunch of fibers are put into a jaw, 2 jaws are there. So, by gripping with the 2 jaws, so bundle of fibers are put, then we try to break the fiber and measure the breaking strength. The jaws are moved out until the fibers are broken. The breaking load and elongation at break are noted. Okay. And tenacity of bundle in terms of gram per tex is measured, is equal to the breaking load in kg multiplied by length of the sample, length of the bundle. We can measure the length of the bundle, different test instrument, their bundle length is fixed. Okay. So, that if we know the bundle length of the bundle, and then what we have to do after breaking, we have to take the mass of the bundle. So, in bundle strength testing, we have to take the mass of the bundle, and then we can convert the strength in terms of gram per tex. So, there are various instruments, those who are measuring the strength and elongation characteristics of bundle. One of them is stellometer. Okay. In stellometer, the name came from strength and elongation, ST from strength, ELO is from elongation. So, the stellometer which measures the strength and elongation of fiber bundle and which works on pendulum lever principle. So, we will discuss the details in the principle of this instrument. Another instrument is there, it is a Presley fiber strength tester. Presley fiber strength tester also works also measures the fiber bundle strength tester, but here the working principle is the beam balance principle. Okay. it is a pivoted beam balance principle. So, these two instruments, stellometer and Presley fiber strength tester, their calculations are exactly same. Even their fiber jaws are interchangeable. Okay. So, that is why a bundle of fibers, that jaw is interchangeable. We can use the Presley jaw also in stellometer sometime. And another instrument that we have mentioned earlier also, in high volume instrument HVI, we test in bundle form, but not like the bundle will not be like Presley or strength a stellometer. Here bundle will be like the comb, directly the comb which has been used for the fiber length measurement, that same comb is used for breaking. It breaks the fiber in comb form. Okay. So, that is in bundle form. Okay. These are the three instruments which measures the fiber, particularly cotton fiber, in terms of in the form of bundle. Now, we will discuss the different terminologies which are used to express the tensile characteristics of textile materials, and these terminologies are, few terminologies are specially for textile materials, but many other terminologies, those are for in general any engineering material we can use. First is that breaking load or breaking strength. This is very general terminology. It is a load at which the specimen breaks. Okay. That is the breaking load. Simple, that is it measures for fiber, it is a centinewton or Newton. So, that type of load, any load measure the, it is at which the specimen breaks. Then stress, stress for any engineering material with specific cross sectional area is measured by force per unit cross sectional area. Okay. But in case of textile material, as we have discussed already while discussing the fineness or linear density measurement, the fibers or any textile materials, they are not circular in nature or as a matter of fact of any normal specific size, neither it is a circular nor rectangular, or it is the cross sectional shape is totally random. So, in case of textile material, we cannot use the stress in terms of cross sectional area, load per cross sectional area. So, cross section of fibers, yarns and fabrics are irregular. So, exact cross sectional area of fibers, yarns and fabrics is very difficult to measure. We cannot measure exactly. Okay. So, we cannot use the term in terms of the stress in terms of mass force per unit cross sectional area. So, this is the typical stress load elongation curve for any fiber or textile material. Okay. Now, try to see here, this is the typical curve I have drawn. So, and this curve is taken from almost this type of fiber. Okay. So, here this is the straight point where the load increasing with the elongation with the linear increase. So, this is the Hooke's region. Okay. After that it is a yield point, then after that there is again there is an increase in the stress load. Okay. And this is the breaking point, and at this point the material breaks. Okay. So, this point if we see, this is the breaking elongation horizontal distance, and vertical distance it is called breaking load. Okay. Let us see the animation here. This is elongation and this one is load. Okay. So, in load elongation curve, at the point where there is a sharp bend, it is called yield point. Okay. And this is a height, it is this is a breaking point, and here from x axis origin, this is the breaking elongation, and this is the breaking load, the y axis distance is a breaking load. Okay. Now, if we see the stress strain curve, this one is the load elongation curve. If we see the stress strain curve, the nature is almost same. Okay. And this the breaking point, at this breaking point, this height is called tenacity. Here it is called breaking load, but here it is called tenacity, that is a breaking stress. Other term is tenacity, and the horizontal distance is known as the breaking strain. So, this is the stress strain curve. Okay. And we can easily convert the load elongation curve to stress strain curve, because if we know, so if we want to convert the load elongation curve to stress strain curve, what are the parameters required? We must know the initial gauge length, initial length. So, that we can calculate the load the stress from elongation. Okay. And for calculating the stress, we must know the linear density, and which linear density? Linear density, that is initial length. Always one should remember, here we have to divide the load with the initial fineness, initial linear density in text. Okay. Because as we increase, as we extend the yarn or textile fiber textile material, the text value changes. Okay. Text value, but we do not take care of that part, we only divide by the initial linear density. Okay. That is the process of measurement. Now, next is that specific stress, that is called mass stress. So, in as we have seen, in textile material we cannot measure the stress in terms of load per unit cross section. Here specific stress is measured by the, it is not the stress, we call it as specific stress or mass stress. In this case, we do not divide by the cross sectional area, we divide it by the linear density. As we have seen, the linear density is proportional to the cross section. So, the value will be actually it is proportional, we will get the indicative value, but the actual, the numerical value may be different, but it is comparative value. Okay. So, in case of textile material, the linear density is used instead of cross sectional shape. So, we can observe in fineness, we have observed that instead of cross sectional area, we have converted it to linear density. Here also in stress, we are converting the stress to specific stress. Okay. So, it also allows the strength of yarn of different linear densities to be compared. So, suppose let us take one example, one textile material say of 10 ticks, has strength of say 100 Newton. Okay. Now, another material of say coarser material of 20 Tex, it has got the strength of 160 Newton. Okay. Now, how can we compare? If yarn was say 10 Tex and the strength was say 110 Newton, then we can say among these two yarn. So, A, B, C, between A and B. So, this A is stronger, okay. That we can say, but if we want to compare A and C, which one is stronger? Because here the complexity is that it is of different linear density. So, to compare this, we convert this strength to the stress, mass stress. So, here the mass stress will be 110 by 10. So, that is 11 Newton per Tex, whereas this yarn C, it will have 160 by 20. So, it will have N 8 Newton per Tex. So, that means yarn A is stronger than yarn C in terms of specific strength, although the yarn actual breaking load is high. Actual breaking load is high in case of yarn C, but the which one is stronger strength wise, the yarn A is stronger, okay, because it has got higher specific stress. So, specific stress is equal to force per linear density, which is initial linear density. One should always remember it is a initial linear density, otherwise linear density always changes. Okay. Now, these are the different terminologies. So, yield stress, yield strain, okay. This is the yield stress, yield strain, tenacity, this I will just discuss. Okay. So, tenacity, what is that? The specific stress at break, that is the tenacity, okay, or specific stress corresponding to the maximum force. Okay. This we should remember. So, we normally get confused, that students get confused that which one is actual stress. Giving a curve, one has to actually identify, one has to calculate the specific stress or tenacity. Okay. Tenacity is specific, either specific stress at break or specific stress corresponding with the maximum force. Okay. Which one is higher, that is the stress. Now, we can see from these two curves. Okay. This is the with the this pink curve, we can see that is this is the breaking point. Okay. Breaking. So, and breaking point is the highest point, that is why this stress we can call it as tenacity. But the curve with the blue curve, where after reaching the maximum point, this we always observe this type of behavior in particularly in staple yarn. After reaching this we observe for filament yarn. Okay. Then because after breakage starts, it does not break catastrophically due to sliding, the slippage of fiber, it also carries some load. Okay. So, after reaching to its maximum point where fibers start breaking, then still it carries some load, okay, for some time. So, here should we take the tenacity as this point or this maximum point? So, answer is that we should take the tenacity for this case as the maximum point. Okay. Next term is that breaking length. What is that? It is the basically the length of the yarn by its own weight, it will break. So, it is a theoretical value. Theoretically, it is a theoretical length in kilometer of specimen of yarn whose weight would exert a force sufficient to break the specimen. So, theoretically, if we see, if we keep on unrolling from the space without any air disturbance, it is a vacuum, if we actually imagine. So, if we keep on unrolling and till the yarn on its own weight, when it breaks, the yarn, that length is known as the breaking length, and it is expressed in terms of kilometer. So, that is why breaking length is actually termed as RKM. Okay? R came from the breaking. So, now let us see 10 Tex yarn breaks at a load of 150 gram force. That is the condition here. One 10 Tex yarn, it is breaking at 150 gram force. What will be the breaking length in kilometer? Okay, breaking length. So, let us see. So, breaking length would be 15 kilometer, because we can see here 10 Tex means 10 gram, okay, 10 gram of yarn length will be 1 kilometer, 1 kilometer yarn length 10 gram, okay. That means 15 gram, 150 gram is the force, gram force will have 15 kilometer. So, 15 kilometer is the 15 kilometer yarn will weigh 150 gram force. It will exert force of 150 gram force. Okay. So, that is why it is called, it is RKM. R came from breaking, and km is kilometer. So, RKM is the term which we use normally, and it is basically numerically the value is exactly same as that the gram per Tex. So, this is the gram force, it is gram force per Tex, this is the gram force 150, we divide it by Tex. So, 150 by 10, it is 15. So, these two terms are exactly same, and we can see in yarn trading nowadays, it is called the breaking RKM value. So, RKM value means we do not actually measure the breaking length, we measure the gram per Tex, and it is called RKM. Okay. Now, we must clearly understand the difference between strain and elongation. Okay. So, what is strain? Strain is the elongation by initial length, that the ratio of elongation and initial length, that is a strain which is actually unitless, but elongation has got the unit of the length, and extension percent or elongation percent, what is that? The elongation and the ratio of elongation and initial length multiplied by 100, this is the extension. These terms strain, elongation, these are used in all any engineering material, any material you can use, it is not specific for textile material. And what is breaking extension? That is the extension at which the material breaks. Now, what is gauge length? Gauge length is another term, it is the length between the jaws. Okay. Original length that of that portion of specimen under test. Now, let us see, suppose this is our fabric specimen. Now, what we do? We use jaws, top jaw, we have gripped here at the top and bottom. What will be the gauge length? Gauge length will be actually actual length of the specimens under test. So, we do not consider the total fabric length, this is the specimen length and gauge length is less than that. Okay. That is the gauge length, that is the original length of the material and between the jaws. Now, when it is extended, suppose it is extended to this point even before breakage, this has been extended. So, still this will be the gauge length, this gauge length is the initial length between the jaws. Now, let us try to understand clearly the details of stress strain curve. What are the different parameters? Okay. We will try to understand with the help of animation. So, here the terms are initial modulus, which is very commonly used in textile material, or Young's modulus. This is the modulus within Hooke's region, where stress is proportional to the strain, straight line. So, up to the point A, this is where there is a proportionality. In that region, if we measure the modulus, that will be the initial modulus. So, it is expressed in terms of it is a tan theta, that means A dash vertical distance by A double dash. This is the ratio where which to express the initial modulus we can calculate. Now, if we extrapolate this curve, this line for easy calculation, that means B dash divided by B double dash. So, this is the stress divided by strain. Okay. So, that is this is the tan theta, okay, initial modulus, the strain by stress. Okay. This one is the A dash. So, strain stress. So, this is A dash is stress and A double dash is strain. So, stress by strain we can get, this curve is stress strain curve. So, initially it is a straight line. So, that is why it is called initial modulus. Another term is called secant modulus. So, initial modulus is one parameter which is actually useful to get the stress strain characteristics at the very initial level, okay, just to the modulus, okay, to know the what is the tough modulus of the material. But during its stress strain path, one may like to know the stress strain, okay, modulus at any point. Okay. That means, the slope of stress strain line drawn between 0 point initial origin, okay, and the any specific point D, okay, of known stress or strain, that is called the secant modulus at that point. So, it is expressed at secant modulus at certain strain, okay, secant modulus of material at say x strain or x stress. So, again at this point we measure the stress divided by strain. Okay. So, that you draw the vertical line stress and then horizontal line stress by strain, that will give us the secant modulus. Now, let us see here. This is the typical stress strain curve. The line is being drawn, okay, with the along with the initial line. A dash is a stress and A double dash is strain. So, here we can see the initial modulus tan theta is a dash by a double dash, b dash or b double dash. Now, this is the point where sudden bend is there. Okay. So, that point is known as the yield point. Okay. This is the yield point, and the distance. So, O O C dash it is a yield stress. Okay. This distance is yield stress, and O C double dash is the yield. So, O C dash is yield strain and O C double dash is yield stress. So, this is the yield point. Okay. So, we can calculate the yield stress and yield strain. This is called yield point. Now, a particular point is drawn. So, secant modulus slope of the straight line. So, this is exactly not showing, but slope of the straight line drawn between zone 0 and a particular specific point D. So, that is how we can get, although it is this animation is not showing the tangent, but it is a tangent we can take. It is a slope at any point. Oh, this is the slope. Okay. And here it is a breaking point. Okay. And this distance, so O E dash is the breaking strain and O E double dash is the breaking stress. Okay. So, these are the terminology we can derive from the stress strain curve. Now, OA elongation is due to, this is OA, this during this zone OA, that is Hooke's region. Here the elongation is due to the stretching of primary or secondary bonds. Okay. That means, it is not breaking the bonds, it is here only primary and secondary bonds are being stretched. Okay. As there is no breakage of bonds, so this will come back, this will return, these are totally recoverable, and this is the Hooke's zone, which is called elastic zone. Okay. Because within this OA zone there is no breakage of bond. Now, once it crosses, what will happen? By further increasing the stress, the curve bends sharply at C, suddenly it bends, where large strain is occurring with the small increase in stress. So, that it bends towards the x axis. So, large strain is occurring with the small increase in stress. This particular point is known as yield point. Okay. And OC dash is yield strain and OC double dash is yield stress. And after this, after the yield point, a plastic flow occurs, breaking some secondary bonds. So, here there will be plastic flow. That means, if it increases, stress is increasing, then there whatever the deformation will be plastic deformation. So, it will not come back, okay, because there are breaking of some secondary bond, okay. And during this, due to breakage, during the breakage of secondary bonds, the molecular rearrangement takes place. Okay. So, what happened? Molecule starts sliding, there will be excess strain due to small increase in stress, but molecular rearrangement takes place during that time. Once the molecular rearrangement takes place, that means molecules are becoming straightened and rearranged once again, then it will again try to impart some stress. So, that in that case the straining will be difficult. So, with the small strain again this stress will increase little bit. So, this rearrangement puts the material in a better position to withstand further stress. So, that means from this point onward. So, here the breakage is taking place. So, from C to say here D point, any other point, if it is asked what is happening between C to D. So, here what happens, the secondary bonds breakage starts, it takes place and molecular rearrangement is occurring. So, this rearrangement puts the material in a better position to withstand further state. So, here the material is little bit in better position, then it's again it's increasing. So, otherwise what happened, if he in this point, so all the molecules starts breaking and the bonds start breaking, then it would have dropped here, it would have failed here, but here molecules are rearranged. So, that means it's again it has got capacity, it gets capacity to actually take more load. So, that is why it is again increasing. The nature of curve, it varies depending on the molecular structure of fiber or yarn. So, depending on the molecular structure, this nature of curve changes. So, there are various factors on which the nature of curve depends. Okay. As the molecular orientation it is more, so then that means the curve will be totally little bit stiff. Okay. Like molecular, if we see the jute and cotton. Okay. Now, let us see. So, these are three fibers, natural fiber. This is for wool, this is for cotton, this is for jute. So, this difference in nature, it is basically due to the molecular structure. Okay. So, depending on the molecular structure, the nature of curve changes. See, wool, polyester, cotton, flax. So, it changes depending on the molecular structure. Flax has got very high modulus, okay, due to the structural orientation of molecule. So, we will stop here and we will continue with this in the next class. Thank you.